Okay, so we have seen how the exponential function can be generalized to include complex variables. We also saw how the logarithmic function appears naturally when we try to invert the exponential function. Using the log function, it turns out that we can also give a meaning to a complex exponent. So that is to say, you take some complex number to some other complex number. Right? So that's what we will discuss in this lecture. Okay, so the starting point is the observation that if you take a complex number and take its power to some integer, then we have this property log of z to the n is equal to n times log z, or equivalently z to the n is equal to e to the n times log z. So this is a property which we have already looked at when we introduced the log function. So this is a result that we will generalize now to allow for n to be any complex number c. Right? So n is no longer restricted to an integer, right? But for any complex number c, we can define z to the c to be this complex number which comes when you compute e to the c times log z, right? So this is chosen keeping in mind the general principle which we have, which is that whenever you generalize a function, it should return for you the same value, at least in the when you put values for which already it was defined. So in this case, if you put c equal to n or c equal to 1 over n, it will return for you the same complex number which we had earlier for z to the n. Right? So of course, because log z is multi-valued, so is z to the c in general. Right? So when c is an integer, we have seen that this is it becomes single valued. But in general, for an arbitrary complex number c, this function z to the c is a multi-valued function. But so like we did with the argument function and with the log function, it is possible to restrict it to what is called a one branch, and consider something which consider, for example, the principal value, right? So there are other values. So at some point we will discuss multi-valued functions in some more detail, but for our purposes here, so we just want to observe that since log z is a multi-valued function, so is z to the c, and we can make it single valued if we restrict log of z to be capital L O G of z, which is the principal value, right? So we can choose z to the c to be e to the c times capital L O G of z, or principal value of log of z, mod z greater than 0, and this angle which is represented by the capital arc of z function is restricted to lie between minus pi and plus pi. And it is possible to choose any range whose which extends over a region of 2 pi, right? But the convention is to choose minus pi to plus pi, right? So if we do this, then it becomes single value. So let's look at an example. Suppose we think of the function z to the I, right? So, and if you wish to work out the value of minus I to the power I, so you might think that this is a very complicated looking operation we are carrying out. So so minus I to the I must be a complex number, right? And however, it turns out that the principal value of this quantity minus I to the power I is in fact simply obtained. So let's look at what happens. If I want to compute f of minus I have to do e to the I times log of minus I, capital L, and log of minus I, to compute it, I have to first put the modulus of this, which is log of 1, minus I times pi by 2. So if it is minus I, then we can ascribe an angle of minus pi by 2 for this quantity, and so then we see that log of 1, right? So it's a real positive number, so log of 1 is just 0, and so we would be just left with I squared minus I squared will be plus 1, so it is just e to the pi by 2. So in fact, it turns out that minus I to the power I, the principal value of this, is a real number, right? So it's e to the pi by 2. So like the log function and the arc function, some familiar laws, relating to exponents may fail if we restrict, this function to the principal value, right? So let's look at an example of how this can happen. So if we consider the same function f of z is equal to z to the I, and if we work out the principal value of f of minus 1, so f of minus 1 is e to the I log of minus 1 by a procedure which is very similar to the previous one, but now we have, instead of minus I, we have minus 1. So e to the I times log of 1 plus I pi, and which is e to the minus pi. In this case, I squared is minus 1, so e to the minus pi. Right. So on the other hand, f of 1 is just 1 because it's 1 to the I. Right. So f of 1 is, you can carefully go over the same argument, but really f of 1 is just 1. It's 1 to the power I. Right. So the key point is that if I take minus 1 to the power I times minus 1 to the power I, and if I take the principal values, I would get e to the minus pi times e to the minus pi, which is e to the minus 2 pi. But this is not going to be equal to, the product of these two functions, these two numbers to the power I, right? So usually we're used to working with, identities like z1 to the power c times z2 to the power c must be equal to z1 times z to the whole power c, right? So this kind of an identity may not hold if you restrict to the principal value, right? So here, for example, you see minus 1 times minus 1 is just 1, so 1 to the power I is going to be 1. So clearly 1 is not equal to e to the minus 2 pi, right? So this is similar to the kind of difficulties we encounter if we work with capital Log of z or capital A arg of z function, right? So some familiar identities involving the log may not quite hold if you're working with the principal value, right? So this function is analytic wherever log z is analytic, and we have seen that log z is analytic everywhere except along this the negative real axis, and so we can use the chain rule to explicitly get the value of the derivative when this function is analytic. So d by dz z to the c is the same as d by dz of e to the c log z, and so you're going to get e to the c log z times c divided by z, which in turn is immediately seen to be just z to the c times c divided by z, or just c times z to the c minus 1, right? So this is the sort of familiar expression we have for, some real variable to some exponent. It's going to give you just that exponent times the variable to the power exponent minus 1. So that's what we are seeing, except now we have both c and z are complex numbers, right? So this function is analytic wherever the log function is analytic, and we have seen how if you choose this branch of the logarithmic function, indeed the log function is going to be analytic, and therefore in this region, mod z is greater than 0, and when argument of z lies between minus pi and plus pi, you have this result. So z to the c is not only analytic, and its derivative can also be explicitly written like here. Okay, so that's all for this lecture. Thank you.